Hi, and welcome to the screencast. My name is Andy, and today I'm going to talk about parsing text in Java. And as an example, we will have a look at Sass files, and this stands for Syntactically Awesome Style Sheets and are another way for generating CSS files. And even though if you're not into web technologies, you can still watch this screencast and learn a lot about how to parse text in Java. So how does this all work? Well, parsing is a part of compiler construction and usually the first step of transforming plain text into something useful. And I've shown the process here in this diagram. So on the left side we have plain text. In our case it's a simple expression. It's 3 plus 4 times a variable called test, and this will be put into the tokenizer, which transforms our plain text into a stream of tokens. And these are shown in the middle, 5 tokens, which are 3, then a plus, then a 4, then a multiplication, and at last there's the variable reference called $test. Now this will be put into the parser, and this will construct a tree, which is called AST or abstract syntax tree. And as we can see, the tokens were still ordered as in the plain text from left to right, but the AST has determined the operator precedence and has constructed a tree according to that. So if we would know what test is, we could evaluate the right part of the tree, which is right here, and we could use this result to evaluate the upper part of the tree, and then we would know what the result of the expression is. So that's the thing we're going to look at today. In our case, the plain text is the Sass sources, and on the output we will construct an AST, which will be then converted into CSS files. As I've said, if you don't care about web technologies, that's alright. We will basically just look at expressions like this, so you should be able to follow just fine. So how does this all work in Java? Well, we'll have a look at this in a minute. Let's first have a look at an example input file and the resulting output file. And then we will go through it from left to right. So we will have a look at the input, how the characters are passed in, how the tokens are generated, and what the parser looks like. So what we see here on the left is an input file in Sass, and this will be converted into the output file on the right, which then will be CSS. And what we can see here, that there are 3 variables defined in the first 3 rows, and we're especially interested in the third one, as this contains an expression and it will be used in this max width parameter. And as we can see, we expect this to be evaluated into the correct result, and that is, we first have to evaluate 960 divided by 12, and then we can add this to 30 pixels, and this should then result in 110 pixels. Alright, but first things first, let's have a look at the input side of things. Our parser will be accepting a reader as input where it reads characters from. But as we cannot always decide what kind of token we are looking at by just looking at a single character, we have a special class which we are looking at right now. And this is called the look-ahead reader, and basically it's a reader which provides an arbitrary look-ahead. And what this means is that we cannot only look at the next character, but without losing any content, we can look at the next and the following characters. And then we can decide when we want to consume those. And the main logic is not defined by the class itself, but by a base class, which is called look-ahead. And we can have a quick look at it here. The main idea is that we have an item buffer where we store our read contents, and we will fill this buffer as needed. So as we can see, we can look at the current character in our case, which calls just next with 0, or we can look at the next character, which calls next with 1, and we can look at any following character, which is just this next method with an appropriate offset. And as we can see here, we simply check our item buffer, and if we don't have enough items buffered yet, we call the fetch method to read a character. And we do this until we either have enough items in the buffer or if we have reached the end of the input. And also this handling down here simply takes care of the fact that if we have reached the input, we will always return the same result, which is a special kind of character in this case, which marks the end of the input no matter with what offset next is called. And next to those methods, which just look at the result, we can also consume a character. And this method is called consume, and it will always pull the current character off the buffer and remove it from there. So if we have a look at our look-ahead reader, we see that it takes a normal reader as input, so we can either read from the console, from a file, or from a network connection or anything else. It just has to be a reader. We now convert it into a buffered reader because we read character by character, so we should have an internal buffer which fills a certain area of bytes to make the read operations more efficient. We then basically implement two methods. The one is the one which creates our special character, which indicates the end of the input, and we will simply return the null character to indicate that. And we have the fetch method, and in this case it just reads from the stream. If we have reached the end, we will return null, and the lookahead class will detect that and return our end of input character, and otherwise we simply return a character object containing our last read character. What we also do here is taking care of the input position so that we always know where we are in the file and we can create informative error messages. Now if we have a look at the type of object which is returned by the fetch method, we see that it's not a normal character object as we know it from Java, but it's a special class which we can see here, and basically it just combines the character value along with its position, which is the line, and the position within that line. And we also have a bunch of helper methods which tell us if our character is a digit or a letter or any other of those things. Now if we have a look at the tokenizer, which converts those characters into tokens, we can also see that our tokenizer extends the lookahead class. So it reuses the same buffer logic and also provides a lookahead, this time not on individual characters but on tokens. So we always know what will be the next token and what will be the following token and so on. Now, just as the lookahead reader, our tokenizer also has to implement the end of input and the fetch methods. So our end of input token will simply be a token which has a special type and which has a special character associated with it. And as we can see, the tokenizer will return token objects as result. And we can have a quick look at this class. And as we can see, a token always has a type, and we especially care about decimal numbers, integer numbers, symbols, which are anything but normal keywords. So every brace or operator or anything is a symbol, and a string is a string constant, and a ID is an identifier, and a special ID is a normal identifier which is preceded by a symbol like a $sign, and we will see later on how this is configured. And the EOI signals the end of input and is a special token. So back to our tokenizer, we can have a look at the fetch method, which is the central method of the tokenizer and is called by the lookahead class to fill the buffer of tokens. And as we can see, it's more or less a simple case decision on what kind of token we're looking at. So the first thing we do is we consume all white spaces because we're not interested in blanks or tabs anymore. The next thing, of course, is if we reach the end of our underlying input, we also return null so that the lookahead class will create and return an end of input token. The next thing we see here is lots of case decisions. So if we currently look at a special symbol which marks the start of a line comment, we simply skip this line and call fetch again and try to parse the next line. The same is true for block comments, so we will also skip those block comments and fetch the next token. Now, a bit more interesting is when we think we are looking at a number, we will try to fetch this number. So let's look at this method first. And the idea is simple. If our current character, which is this right here, is a digit, or it's a minus sign, and the next character is a digit, and we can see the use of current and next here, so we won't consume the minus sign from the input. We will just peek a look at the character after that and check if that is a digit. In that case, we're looking at a number. In any other case, it's just an operation. So if is at start of number returns true, we are definitely looking at a number, and we will enter the fetch number method. And as we can see here, we create an appropriate token with the type integer, because we still believe we are looking at the integer number. We initialize it with the first character with its position, and then we start to parse it by adding the first character to the content. We then iterate over the input, and as long as we are reading either digits or a decimal or grouping separator, and after that comes another digit, we consume this input. And as you can see here, we have another decision. So if we're looking at a grouping separator, we want to preserve this information, so we add it to the source value of the token, but we do not add it to the content. And there's a fine distinction between those informations. So a token always knows its source, like the exact representation in the file, and it also knows its content, and that is the relevant part of the source, which makes up the token. And for our case, we don't want the grouping separators in there because we want to convert it to a number afterwards using the standard Java functions, which don't like grouping separators too much. What we also can see here is that once we encounter a decimal separator, we normally just create another token, which is a decimal token in that case, and we copy the contents over to our new token. Now, if we already have seen a decimal separator, our token type will be already decimal, and we will report an error. The key thing here is we do not throw an exception and we do not abort processing. Rather, we just report an error to our internal error or problem collector, and this is simply a list of parse errors, and a parse error is always a position and an error message, and all those errors will be collected, and we will try to ignore it as long as we can, and once the parsing completed, we will report as many errors as we can so the user can fix those all at once, and we do not abort processing just because of one missing semicolon or things like that. So if we jump back to our fetch method, we can see that this scheme is throughoutly followed. So we've been looking at how to parse a number, and the same is true how to parse an identifier. So we have a set of certain start characters, and once we see them, we simply read all of the matching characters until we believe the identifier is terminated, and this will most commonly either be a white space or a symbol character or the end of the input. And basically that's all the tokenizer does. So we can see here, right here is the end of the fetch method, and in case we encounter anything we cannot handle at all, we also add it to the problem collector and simply throw it away, kind of ignore it and call fetch again, and will hopefully fetch another token, which then can be processed. So that's all the tokenizer does. And now we'll have a look at a parser. Alright, what we're looking at here is the parser class, which takes care of parsing Sass files. Now, when it comes to parsing, there are basically three alternatives. The first is building a recursive descending parser, which is the simplest approach, which we also use here. The second one is using a so-called parsed parser, and those are more flexible, as you can define a grammar and a matching parser is constructed at runtime. The good thing is they're quite flexible. The bad thing is they might consume a lot of memory or might have a bad runtime behavior. The third kind is to use a special parser construction tool, and the benefits of doing so is you can have an extremely flexible grammar and a highly optimized parser for that. And the downside of that is that it's really complex to construct a valid grammar for such a generation tool. And also you have to learn another language which describes the accepted grammar. So in our case, the grammar is quite simple, so we'll stick with the recursive descending parser as they're really simple to implement. What we can see here is that we have a special kind of tokenizer, which is called a Sass tokenizer, and this is used to configure the tokenizer class as we need it. So we set up what kind of keywords are there, what kinds of comments are accepted, and what symbols start a special ID. So if we encounter a $sign, we know that the identifier behind this will be a variable. All the other methods which are declared here specialize the tokenizer even more to work with Sass files correctly, but we will skip over that and directly head to the parse method, which is the central entry point for our parser. So in the parse method, we can see the basic idea of a recursive descending parser. What it does, it simply loops until there's something more to read, and this will check for anything but the end of input token. And based on what token we currently looking at, so we check the current token of the tokenizer, we then decide what we want to do. So if we see an import keyword, we call a special method which handles an import statement. If we see a mixin keyword, we handle the mixin statement, and so on. And that's the idea of a recursive descending parser. So it's recursive because those parse method might call itself, which we will see later, and it's descending because it will always call a more specialized method, which will then take care of parsing the contents. Now what we are interested in is parsing expressions, and therefore we'll have a look at the parse expression method, and it's always a good thing to name the methods just like their job. So if we're parsing in expressions, we name the method parse expression. And what it does is quite simple, as in our case an expression is either a constant value or an operation. So what we do first is we call parse atom, and an atom is anything that cannot be split any further. So it might be a numeric constant or an identifier or anything like that. Now, if we have a look at the implementation of parse atom, we see that if the tokenizer is currently looking at a number, we simply return a number node to be processed further. And what also is interesting, if we're looking at a special identifier, which was started by a $sign, we know that this is a variable, so we return a variable reference as result. And even more interesting, if we're looking at a praise, we know that this will be again an expression, so we call parse expression, and this is the recursive part because parse expression called parse atom, and parse atom again calls parse expression to parse the inner expression. And After that, we expect a closing brace. If our expectation is not matched, we again add an entry to our error list and still try to continue parsing and just ignore the missing bracket right now. If the expression we parsed was an operation, we set a special flag on that to protect it from reordering. And we'll have a look at that soon, because reordering takes care of operator precedence. So if we jump back to our parse expression method, we see that we parse an atom, and then if our next symbol is a plus or a minus sign, we simply call parse atom again to pass the right side of the operation, and we create an operation node for our ast. On the other hand, if we have a multiplication, division or modulo operation, we save the operator and also parse the right hand side of the operation, but then we call a special method which will take care of reordering to match the operator precedence. And as we're in a while loop, we will do this until we see a special symbol, which is defined here, and this must not be an exclamation mark, and this again has internal reasons for Sass parsing, but basically as soon as we see anything but a valid operator, we will break our loop here and return the parsed expression. Now let's have a look at operator reordering. And this is what the join operations method does. It tries to reorder the operands so that the operator precedence is handled correctly. And although the code is quite short, it's a bit complex, so let's look at this on a slide. Now what we're looking at here is the token stream of our example expression, and when our parser enters the parse expression method, it will call parse atom, which will return the first number 3. It will then detect the plus sign and treat that as operation, so it will call parse atom again for the right hand side. This will return the number 4, and as a result our operation 3 plus 4 will be generated as part of the ast. Now our while loop continues and we will see the multiplication, and therefore our parse atom method will be entered again. Now with this parsed right hand side we have our multiplication operation and our previous expression 3 plus 4, and also the multiplication with test is passed into join operations. Now this will detect that the operator precedence is not matched correctly, so we cannot just continue, but we have to exchange the operands, and therefore it will take the right hand side of the plus operation and add this to the multiplication. It will then take our newly constructed operation 4 times $test and use this as the new right hand side of our plus operation. Now our ast matches the operator precedence of the expression. As the lower side, 3 times $test will be evaluated first, and then 3 plus the result of that will be the result of our overall ast. So that's the whole magic of the join operations method, which takes care of operator precedence. Now after quite a bit of theory, let's watch this all in practice. I've shortened our example input a bit, so it's just the expression which we see here, and we will now inspect this using the debugger. And I've already placed a breakpoint in parse expression. We trust the tokenizer to do its job, so let's have a look at parse expression. And what it first will do is call parse atom, so let's jump in there. And now we can see the tokenizer is currently empty. Let's make it fetch a token. And as we can see, the tokenizer fetched a first token and checked if it is a number, and as we see here it's 30 pixels, which is in Sass a number, so we will return this number as first operand. Back in parse expression, we will check if there's more input. Yes, there is. We will have a look at the next symbol, which is a plus sign. So we jump in there. And now to parse our operation, we pass the right hand side. So we enter parse atom again. Again, we will check if it is a number. Again, we will check it if it's a number, and 960 pixels is a number again. So let's return that. And now, as we can see, our result is the operation 30 pixels plus 960 pixels. We check if there's more input. Yes, there is. We check if the next symbol is a plus or a minus sign, and as it is a division, it is not. So next we check if it's a multiplication, division or modulo operation, and yes, it should be. So we enter this if block, we read the operation, it's a division sign. We parse the right hand side, so let's jump into parse atom again, and as we can see now, it is again a number, in this case 12, so let's return that. And now next is representing the number 12, and now let's enter the join operations. So we check if we're looking at an operation. Yes, we do. So let's fetch this. And now we're looking at our most right hand operation of the left side. It's a bit confusing, but it is our plus operation 30 pixels plus 960 pixels. Alright, now we check if this is protected by braces. It's not. And we also check it if it's a plus or minus operation, because those have the lower precedence, and this will be true. So we enter this operation, and this quite complex looking line is now doing the operation reordering. So if we execute this, we now can see that we're looking at a plus operation, which left side is 30 pixels and which right side is again an operation of which the left side is 960 pixel and the right side is 12 pixel. Now let's check if there's more input. Yes, there is, but we see the current symbol is a semicolon, so it's not a plus or minus operation. It's also not any other operation. So it is a symbol and also no exclamation mark. So we enter our loop, we exit our loop here, and our result is the overall expression as expected. Now that we've seen the parser in action, let's finally have a quick look at what we've created. And the main class of our AST or abstract syntax tree was the operation class, which is what we are currently looking at. And as we can see, it has a left hand side and the right hand side. It has the protected flag, which determines if our expression or operation was protected by braces. And if we want to obtain the result of this operation, we can have a look at an eval method, which takes a scope defining all variables, and a generator, which is in charge of generating the output. And as we can see, it's a bit complex looking, but the idea is quite simple. We first parse our defined values, and this is a bit complex because we have to cut off the units, and based on the operation we now execute the matching operation in Java, and then we match our units and create a resulting output number for our expression. So I hope you've enjoyed this quick look through the service Sass parser. If you like it, give it a thumbs up and catch you next time.